Hello, my name is Shivdath, and today we're going to look at a Gaussian integral and how to compute it. So the Gaussian integral really is the integral over the entire real line of e to the negative x squared dx, x ranging from negative infinity to positive infinity, in other words, over the entire real line. It's also called the Euler-Poisson integral. Now this shows up all the time when we're, for example, when we're dealing with normal distributions, distributions which look like that, the bell-shaped curve, where we have a majority in the center, and as you kind of go to extreme values, extreme lows or extreme highs, the number of occurrences tapers off. For example, many properties which show this distribution. For example, human height or any quality of human beings, right? The majority are going to be in the center, and as you go for extremes, extreme heights, like 7 foot and above, and maybe 4 foot and below, you're going to have very few people who meet those criteria. It also shows up all the time in the error function. In physics, for instance, when you have an error. Now we're going to look at how to compute this. It's interesting to note that the indefinite integral without the limits doesn't have any solution in terms of elementary functions. In other words, there's no way to really simplify this. But we can find an answer to this using a neat trick. So what we're going to do is, let's just square this, right? Let's square this value. So this is equal to the integral negative infinity e to the negative x squared dx times the integral negative infinity to infinity e to the negative x squared dx. So you agree with this, right? I've just multiplied the two terms. I'm squaring it and multiply the two terms. But now, instead of x, right, let me just replace the variable x by y. That should make no difference because these are evaluated separately, and this is just a variable, what's in a name. So I can do that. And now combining them again, that would equal to e to the negative x squared plus y squared dx, integral negative infinity to infinity. So what we're trying to do here, do you see what the idea is? We're really trying to change our coordinates from Cartesian coordinates x and y to polar coordinates. In case you need a refresher, if this is our xy plane, right, any point in the plane can be represented by its x coordinate and its y coordinate. Those two values uniquely determine the point. But we can also determine the point uniquely by its distance from the origin, which we'll call r, and the angle theta it makes with the x-axis. So representing the point in terms of r and theta is called polar coordinates. And notice that distance r, right, is nothing but x squared plus y squared, the square root, the Euclidean distance, is from a Pythagorean right triangle, right? If this is our point, this is the x value, this is the y value, this is the r value, we have a right triangle, we can calculate the value of r in terms of x and y. Similarly, we can calculate the value of theta in terms of x and y, and using some trigonometric functions like sine and cosine. Alright, so x squared plus y squared is nothing but r squared from that right triangle. So this turns out to be, and sorry, this is dx, dy, right? We're just integrating over the entire plane. But this is nothing but integral e to the negative r squared dr, dx, dy, converts to r dr, where r dr d theta. So dx dy goes to dr d theta, and we have that extra factor r in there, which is called the Jacobian. This is from simple multivariable calculus. When you're changing coordinates, you have to multiply the integral by the Jacobian, which we can discuss in another lecture. And notice that theta is going to range from 0 to 2 pi, and r is going to range from 0 to infinity. Right? R is never negative. R is the distance from the origin, which can only be 0 and can go to infinity, while theta goes from 0 to 2 pi all the way around the circle. Now notice that theta is independent of the r. There's no mixing, so we can write this as 0 to 2 pi d theta times. Now what if I write r squared as s, right? Now that'll give me e to the negative s, and dr is, so if r squared equal to s, 2r dr by ds equal to 1. Also 2r dr equal to ds. So dr is equal to ds by 2r. So I get r, and dr is ds by 2r. ds by 2r. Sorry, bad handwriting. And then I have I have the d theta already. So I just replaced r in terms of s. Notice this r and this r cancels, and I'm just left with this 2. And integral, and notice r goes from 0 to infinity means s also goes from 0 to infinity. So I get 2 pi from here. D theta integral just gives theta from 2 pi to 0 to 2 pi gives 2 pi times half integral of e to the negative s from 0 to infinity, which is going to be nothing but 1 upon e it's not going to be nothing but e to the 0 minus e to the infinity, which is going to be, or rather 1 upon e to the 0 minus 1 upon e to the infinity, because we have the negative sign, minus 1 upon e to the infinity. E to the 0 is 1, e to the infinity is infinity, so this is 1 minus 1 upon infinity, or 1 minus 0. So this is nothing but pi. But notice that we had squared what we wanted to find in the beginning, right? We wanted to find this, and we took the square of that. So our answer really is going to be the square root of pi. So if you had a chance to internalize all these calculations, what we're really saying is that the value that we wanted to calculate in the beginning is the square root of pi. And this is the final beautiful result. What's really interesting about this is that, again, there's no closed form, no elementary functions that can define the indefinite integral if you don't have the limits. But the moment you put the limits on there, you can get an answer using a neat trick, a neat substitution to polar coordinates. And also, this Gaussian integral shows up all the time in physics is replete with examples, math too, pure math. And also it shows a very nice connection between Euler's constant E, the constant pi, and calculus, integration, which is kind of reminiscent of a lecture in which I discussed the most beautiful math equation, e to the I pi minus 1 equal to 0, or plus 1 equal to 0, where you see a relation between e pi, I, and the fundamental operations of math, like equal to plus, multiplication, and so on. Well, I hope you enjoyed it. Thank you very much.